So now we're going to have a look at some questions from the 2022 HSC Standard 2 paper. So this is quite a recent Standard 2 paper. This is the more basic course than Advanced Maths. So for any students taking this, obviously you've got Standard 1, Standard 2, Advanced Extension 1, Extension 2. This is the standard which has the mandatory exam. So let's start. Let's have a look at the multiple choice questions. So question 1, we have which graph represents a negatively skewed distribution? Well, anything that's symmetrical is not skewed. So A and B are not skewed. If we have a look at C and D, it's got to be one of these two. One of them has the hump to one side and the other one has the hump to the other side. Well, as it turns out, the direction of the skew is where the tail goes. So this tail is going towards negative values, and this means this is a negative skew. This tail is going towards positive values. This means this is a positive skew. So, or this would be larger values. The tail covers larger values than the rest of the distribution. And for question 1, this tail covers smaller values than the rest of the distribution. And so this means, in fact, the answer is C. Right, so now we'll have a look at question 2. So we have, which of the following could be the graph of y equals minus 2x plus 2? So y equals minus 2x plus 2 has a slope of minus 2. That means it's going down to the right and it's fairly steep. And it has a y-intercept of plus 2. So this is where we're getting the minus 2, this is where we're getting the plus 2. That means it cuts the y-axis at the value y equals 2. If you look at these graphs, C and D are not possible because they slope up to the right. B and A are possible because they slope down to the right. B is not possible because it cuts the y-axis at a negative value. So therefore the answer to this question must be A. So now we'll do question 3. The network diagram shows the time needed for each step in order to complete a project. What is the critical path to complete the project? So for this question, we have to remind ourselves that critical path in the case of these diagrams is essentially the longest path. So we are looking for which path, when we traverse through the diagram, is longer than all the others. Now we know that it's going to be one of the listed ones, ACI, ADG, BEH, BEFG, because they're given to us. So we need to check the values associated with these paths, pick the longest one, and that will be the critical path. You don't have to do this. You could just sort of test different paths on the diagram. There's some methodologies to find critical paths, but the easiest way to do this is just add them up, pick the biggest one. So we have ACI. This takes us along path A, then path C, then path I. So this is 3 plus 13 plus 2. So this is 18. Yep. And then we have path 2. This is ADG. This takes us along path 3, then 16, then 3. This will be 3 plus 3 is 6 plus 16 is 22. Then we have path BEH. This takes us along 2, then 9, then 6. 2 plus 9 plus 6. This is equal to 16. And then our last path, our fourth path, we have BEFG. BEFG. This is 2 plus 9 plus 2 plus 3. 2 plus 9 is 11, 2 plus 3 is 5, they add to make 16. The longest of these is ADG, which is 22, and so therefore ADG is the critical path, so the answer is B. All right, so now we'll have a look at question 4. So we have Lily wanted to estimate the number of fish in a lake. She randomly captured 30, tagged them, released them. 1 week later, she randomly captured 40 from the same lake. She found that 12 of the 40 were tagged. What is an estimate for the total number of fish in the lake? So this is the capture-recapture technique. So when you initially capture and tag a certain number, you get a ratio. Tag over population. You know the number you've tagged. You don't know the number in the population. So you collect fish, you tag a certain number, there is a certain population. You assume this is equal in ratio to the number that were tagged when you collected them divided by the number collected. So you collect a whole bunch of things from a population, you tag them, you release them back, you know this number, you know tag 1. Then you come back at some later time, collect things again. Some of the things you recollect will be tagged. These are what you will call tag 2, and the total number you collect will be this, the collection. And so these form an equation where you only have one unknown, which is the population. So if we plug all of our numbers in here, we have 30, the number that she tagged, over population, which is unknown, is equal to 12, the number of fish when recollected were tagged, divided by 40, the number of fish she recollected. And we need to solve this for p. So we get multiply both sides by 40. We get 1200 over p is equal to 12. Multiply both sides by p. This gives us 1200 is equal to 12p. Divide both sides by 12. This gives us p is equal to 100. And this is the solution we get in this case. This is D. Remember, this is a capture-recapture technique, so this is just an approximation, right? If you're actually doing this in the real world, you're collecting birds or fish or customers or whatever it happens to be, and you're trying to estimate populations, you're very rarely going to get exact values. Probably almost never if you have large enough samples. But this number is an approximation. So that's why the question says, what is the best estimate? The best estimate is 100, which is D. Okay, so now we'll have a look at question 5. Question 5. Consider the following data set. 13, 16, 17, 17, 21, 24. Which row of the table shows how the median and mean are affected when a score of 5 is added to the data set? All right, so let's just draw our little list here. 13, 16, 17, 17, 21, 24. So the average of this data set, we could calculate it. We don't really need, well, we may as well. It's not that hard. We don't have to, but we may as well. 13 plus 16 plus 17 plus 17 plus 21 plus 24 divided by 6 is 18. So the average here is 18. The median, which is the score in the middle, or if there's 2 in the middle, the average of the scores in the middle. Well, they're both 17. The median is 17. So for data set 1, this is what we have. We have a mean of 18 and a median of 17. If we add 5, so now we have a new data set 2, and this is 5, 13, 16, 17, 17, 21, 24. Immediately we know the mean is going to be lower because we're adding a lower score. So we can calculate these. So calculate the same thing we did before, but now we have a 5 and now it's divided by a 7. So this gives us 16.1428 ... So 16 and a bit. But the median is still the middle score, which is actually still 17. There's now just one median. There's one value in the middle. It's 17. So the median hasn't changed. So we know the mean changes. In fact, we know the mean goes down, but it changes. And we know the median stays the same. So if we have a look at our four options, A, they both change? No. B, they both stay the same? No. C, median changes, mean stays the same? No. D, median stays the same, mean changes? Yes. So the answer to this question is D. And you didn't actually have to calculate these. You should be able to calculate these fast enough for this to be entirely viable. But just by looking at what happens, you can see the median remains the same. And whenever you take a data set and you add extra values to it that are lower than the mean of those new data sets, the mean of the new data set is lower. So if you have 1, 2, 3 and you add an extra 1, the mean of 1, 1, 2, 3 is lower than the mean of 1, 2, 3. If you have a data set 1, 2, 3 and then you add an extra score, 10, the mean of 1, 2, 3, 10 is higher than the mean of 1, 2, 3. Right? Whenever you add an extra data point which is higher or lower than the mean of an existing data point, it changes the mean in that direction.